Good afternoon, class. We're going to finish off chapter 9 with section 9.4. We're going to skip section 9.3 and look at 9.4, comparing two population proportions. Recall that in section 8.4, we stated that the population proportion P related to our binomial probability of success. That is, P is our population proportion. Again, it is highly unlikely that we can calculate our population proportion. So we use our best point estimate, our sample proportion, and we label this as our p hat. Note, this is exactly the same formula we would use for our population proportion. However, all values come from our sample data instead of our population data. Just as we constructed a confidence interval for the difference between two population means, when comparing two population proportions, we use a confidence interval for the difference between the population proportions. This is because we can easily see if they are equal or if one is larger than the other. The best point estimate for the difference between two population proportions, P1 minus P2, is the difference between our sample proportions, P hat 1 minus P hat 2. When the samples taken are independent, simple random samples, the conditions for a binomial distribution are met for both samples and the sample sizes are large enough, the margin of error of a confidence interval for the difference between two population proportions is given by this ugly looking formula, right? This is a very long formula, but again, we're going to utilize our calculator, so don't be afraid of this formula. The confidence interval is given as follows. We've seen this already from chapter 8 all the way through sections 9.1 and 9.2. We're just going to change our point estimate. We're talking about the difference between population proportions, so our point estimate is the difference between sample proportions. So we subtract our error to get our lower endpoint of our interval, and we add our error to get our upper endpoint of our interval. Let's look at an example. In order to determine if a new instructional technology improves students' scores, a professor wants to know if a larger percentage of students using the instructional technology pass the class than the percentage of students who did not use the new technology. Records show that 45 out of 50 randomly selected students who were in classes that used the instructional technology passed the class, and 38 out of 51 students who were in classes that did not use the instructional technology passed the class. Construct a 95% confidence interval for the true difference between the proportion of students using the technology who passed and the proportion of students not using technology who passed. And we want to interpret our results. Now, pause this and try to attack the problem. I know we haven't done an example together, but again, it's very similar. We're going to need to pull out our idea of population 1 and our idea of population 2. What do you think population 1 is going to consist of? What group do we mention first? If we look, we mention students who were in classes that used the instructional technology that passed the class. So our first group we're going to focus on are the students that used the technology and they've passed the class. Our second group are going to be the students that did not use the technology but still passed the class. Okay, so now we've separated those, and we need to find a few things. We need to find our sample proportion, our p hat 1 and our p hat 2. This involves finding our sample sizes, n1 and n2. So you should have calculated the following values. P hat 1 is 0.9, and we can see that here. 45 over 50. right? This gives us 0.9. And then p hat 2, 38 over 51, which gives us 0.745098. We should also see that our point estimate is the difference, p hat 1 minus p hat 2. Well, p hat 1 is here, p hat 2 is here, so when we subtract, we get 0.154902. We're going to use this number at the end of the problem. Now, we need to calculate our error. So in our error, we need a sample size for the first group and a sample size for the second group, and we need a critical z-value. So in the problem, we notice that we're looking at a 95% level of confidence. So our critical value using table B is 1.96. So plugging all of the values into our formula, we have 1.96, and then our p hat 1, which was 0.9, and then our p hat 2, which was that longer decimal, 0.745098, and then our N1 and N2, so N1 was 50 and N2 was 51, we get the margin of error to be 0.145675. And now, putting all of this together, I'm going to use my point estimate and my error. Subtracting these values, I get 0.009. Adding these values, I get 0.301. So here's my confidence interval. And if we want to interpret it, notice that these are positive values here, right? Positive values means that this one is larger, or should be larger, right? A larger number minus a smaller number gives us positive numbers. So this tells us we're 95% confident that the proportion of students who passed using this new instructional technology is approximately, if we think of these as percentages, 0.9% to 30%, right? Moving the decimal over, 0.9% to 30%, higher than the students who did not use this new instructional technology. As always, if you have any questions, please post in our Canvas discussion board or send me an email, okay? The hardest part about this exam is not doing the problems, but it's that the problems are all mixed together. I highly encourage you to look at our course announcement on how you can create practice exams in the Hawks learning software so that you can get used to mixing the problems up and seeing if you can distinguish between different types of problems and when to use the appropriate formula. Because in the homework, we use, 8.1, we use the 8.1 formula. 8.3, we use the 8.3 formula. 8.4, we use the 8.4 formula, so forth. The exam is going to have all of these problems mixed around, and you're going to have to read it and ask yourself, what am I trying to estimate? What do I want a confidence interval for? Do I want it for the mean? Do I want it for the proportion? Or do I want it for the difference between means or the difference between the proportions? The second step is that if it's a problem about the mean or difference of means, we have to ask ourselves, is sigma known or is sigma unknown? Okay? These are the important steps to reading and solving these types of problems.